Assalamu alaikum. Welcome to my channel M.Asif Math Corner. Today we will discuss that if G is an abelian group and H has a finite order elements in G, then H is a subgroup of G. Let's start. Theorem is G is an abelian group. What the means abelian group is that commutative law hold in G and H be the set consisting of elements of finite order. We have a lecture on the order of element. We know that what is the order of element? Order of element is means that the which power of element, which the least power of that element give us identity. For example, in a group we discussed that 1 minus 1 iota and minus iota. The 1 was the identity element and iota power 4 give us identity element 1. It means that the order of element iota is 4 and minus 1 power 2 give us identity element. It means that the order of minus 1 element is 2. I hope you understood what is order of element. If you want to take the complete lecture about order of element, then you can find the lecture in my channel M.Asif Math Corner. So let's start the proof. Let A B belongs to H. Then there exists integer M and N, as we discussed earlier, that the H consisting the elements of finite order. So these are finite numbers. M and N are finite numbers. So the A raised to power M give us identity and B raised to power N give us identity. Because M is the order of A and N is the power of B, order of B. So the order of element give us the identity element, and AB raised to power Mn, if we combine these elements, then it is AB dot AB dot AB Mn times. Then by taking raised to power on both separately, then A raised to power Mn and B raised to power Mn, which give us A raised to power M raised to power N and B raised to power N into M. We know that A raised to power M give us identity element because order of A is M. So identity element E raised to power N and B raised to power N, order of B is N. So it also give us identity element. So identity element has inverse itself. That's why any power of identity element give us identity element. Whatever the order M or N is. For example, power of 2 of 1 give us 1. 1 raised to power 3 give us 1. 1 raised to power 4 give us 1. The identity has, if any power, it give us identity itself. I hope you understood. Let's check next. Now, as A has finite order, B has finite order, so AB has also finite order in H. Here we proved that identity element is present in H and AB means that commutative law also hold, and now we are going to prove that inverses are also present in H. So if B belongs to H, then b raised to power n is equal to identity element because the order of b is n. Then b raised to power minus 1 into n, b raised to power minus 1 take n times b raised to power n minus 1, b raised to power minus 1, b raised to power minus 1, up to so on. So it is because it was n times, so b raised to power minus n, or we can write it b raised to power n minus 1, or you may say that b raised to power n inverse. So we know that b raised to power n is equal to identity element because n is the order of b. So identity element raised to power minus 1 or inverse of identity element is a self-inverse because 1 divided by 1 give us 1. So here we prove that inverses are also present in H. So it's proved that B inverse also belongs to H, hence H is a subgroup of G. I hope you understood. Thank you so much.